for joining us on this video on PID tuning. It's roughly about 20 minutes or so. So we'll get going. If you have any questions, we can get to those at the end.
Welcome to today's tutorial. Let's get started. Let's take a look at our agenda for today. Today we are looking at PID tuning on the Horner OCS. The idea for this webinar comes from a question we received from a customer, which was, how do I tune a PID loop when the output of the loop is a digital variable instead of an analog one? So first, we'll do a quick review of PID control and the Horner PID instruction. We covered these in a webinar called PID Control in Horner All-in-One Controllers, which you can find in the webinar section on the Horner website. Next, we'll look deeper into PID tuning methods. We'll also look at what are the implications of using a digital outpush to control a process versus an analog one. We'll have demonstrations throughout, and as always, we'll finish with a Q&A session. PID is a mathematical approach to process control. On the screen, you'll see equations for the traditional form of PID and the ISA form of PID, which are the two that we've implemented at Horner. Keep in mind that understanding your process is more important than understanding all the details of the math. So just note here that there's three elements to the PID algorithm: proportional, integral, and derivative, and each of those offers something different when it comes to controlling your process. We'll talk about that more as we go on. Let's look at the process itself. Process control is the automated control of a process. Here there's some terms that you need to be familiar with. First, the process variable is the variable that's being measured or controlled in the process. So for an oven, for example, that could be the temperature of the oven. The control variable is the variable that we manipulate that will cause the process variable to change. In our oven example, that could be a gas valve that's controlling the flow of gas to a burner, which controls the temperature of the oven. Next, we'll talk about the set point. That's the desired value for the process variable. The error term is the difference between the desired value of the process variable and its actual value at any given time. Finally, the controller is the equipment that's tasked with controlling the process, which in our demonstration is the Horner OCS. There are several goals for a controller when it comes to PID or process control. You want to get to the set point fast, you want to get all the way to the set point, and you don't want to overshoot by too much. We have our proportional, integral, and derivative available to help us in that effort. The proportional will help us get there fast, the integral makes sure we get all the way to the set point, and the derivative is useful to make sure we don't overshoot by too much, and to make sure we're as stable as we need to be. So the goal of PID from a tuning standpoint is all about selecting the coefficients that will help us balance the proportional, integral, and the derivative to control our process the way we need to. Now let's talk about the Seascape PID instruction. We have two variations available, an independent version and its ISA version. It's based on integer-based math. You don't have to have floating point capability to do an excellent job of doing PID control. Our PID instruction requires that you allocate 16 registers or an array of 16 variables to it as additional resources. The algorithm supports auto-tuning using a modified version of the Ziegler-Nichols open loop method. The PID instruction can be used to control either digital or analog values. When you put a PID instruction in your logic and you configure it, obviously you have a main configuration dialog box with many different parameters. We won't go into detail on these. We'll go into some detail in our demonstration, and there's additional detail in the PID webinar I mentioned earlier. The bottom line here is this is where you configure where the set point's coming from, what is your process variable, your control variable, etc. Also note that when you use a PID instruction in your logic, you almost always are going to leave it on all the time. Even when you want to manually control the output, you're not taking power away from the instruction. Instead, you put it into manual mode through the use of a manual variable that's been assigned to the block. Then you can temporarily manually control the output, and then when you're ready, you can put it back into automatic. There's also Autotune parameters to configure. That is a bit that triggers the Autotune process, and another bit that you monitor that says that it's done. If you're not using Autotune, then you don't need to worry about these parameters. For those 16 words that need to be allocated to the instruction, the chart on the right there shows all the detail on what's included in those 16 words. Again, we'll look at that during the demonstration, and there's additional detail available in that PID webinar. One of those words is the config word. Additional details on the config word are shown here. It's a bitmapped word of about 12 bits to help you do some of the configuration of some bit type parameters. We'll talk about that again in a moment. Now let's look at the implications of using a digital outpush to control a process. First, why would you use a digital outpush to control the process? For that, let's talk about an example of a pizza oven. Let's say we have a gas pizza oven, and in this example we want to control the temperature of the oven by varying the amount of gas that's being provided to the burner. To do that, we'll adjust a proportional gas valve between 0 to 100%. That's an analog actuator we'll be adjusting in the case of a gas pizza oven, but for an electric pizza oven where we're using on-off control to regulate the heat, in order to add heat to the system, we're turning an electric heating element on and off. So the control of that heating element is a digital signal. The implications of that from a setup standpoint are as follows. First, you start out by setting up your PID loop as you normally would, but then you'll make some adjustments at the end for a digital outpush type process. First, you need to add an output coil to your PID instruction. On the screen I have one called heater SSR. You need to add that for a digital output process. Then you need to tell the PID instruction that it's being used with a digital output. To do that, bit 15 of the config word that we looked at earlier needs to be set to tell the algorithm that we're using digital output control. Next, we need to consider the output cycle time. If you need to increase the time between on-off cycles to avoid mechanical wear of your actuator, for example, then you can increase the PID cycle time parameter in seconds. Finally, you must set the upper clamp to 32,000 and the lower clamp to minus 32,000 if you're using a digital output to control your process. At runtime, the OCS PID loop will calculate an integer value for the control variable, or the CV for short. It's going to turn the output on if that control variable value is 0 or above, and turn it off if that value is negative. Next, let's talk about different PID tuning methods. Again, the idea of PID tuning is to select the coefficients that will allow the right amount of proportional, integral, and derivative control in the algorithm to adapt to your process. The first method we'll look at is manual tuning. Here, you'll start out with zeroing out the coefficients for P, I, and D, and then you just put in a value for your proportional term, and then you'll execute that value for proportional only control as the first experiment. You can just put a value in, or you can try and calculate a value for that. For calculating that, you can take advantage of the fact that the control value equals the proportional coefficient times the error term. For example, in our pizza oven, as we're heating it up, we want the heater to be on full blast, or the maximum control value, until we get within 5 degrees Celsius or so of the set point. We can take advantage of that formula, and we can determine that the maximum on our control variable is 32,000 counts, and if 5 degrees Celsius is scaled in our application to 500 counts, then once we have them both scaled to count, we can do the math, and we get an initial KP value of 64, which would be a good starting point. Then with this method, you need to let that value run, and you need to find out if it works for you. Then you can increase it if things are taking too long, and you can decrease it if you're overshooting by too much. And you do that until you have dialed in your KP term relatively well. Next, you'll add an integral. Typically, you don't need a very big value here. Generally, the integral will help you get all the way to the set point, so if you're getting stuck above or below the set point, then you can add an integral to help with that situation. Once you've tested it and you're happy with your integral, then you can add some derivative in to help improve your overshoot and improve your settling time. So that's the manual tuning or experimental type approach. You can also take a mathematical approach by taking advantage of the Ziegler-Nichols tuning experiment. Here, you basically let the process run with a certain procedure, and while that's happening, you'll record some values for the purpose of determining some time values. Once you've determined those time values, you'll input those into the equations on the lower right to come up with your initial coefficients for P, I, and D. Now let's look at the process that's used for auto-tuning with our PID algorithm. That's a modified version of the Ziegler-Nichols method. First, the control engineer puts in an appropriate set point value for the experiment. The first thing that happens is the OCS sets the control value at maximum, which drives things up towards the set point. As soon as it exceeds the set point, that control variable is driven to minimum or minus 32,000, causing it to drop below the set point. When it gets below the set point, then one cycle is complete. The OCS continues that process for 3 complete cycles, and based on those experiments, it calculates the P, I, and D coefficients. Now let's begin our demonstration on PID tuning. So here's my test setup for our PID tuning experiment. I have a bowl with half a litre of water in it. I'm going to heat the water. I have an immersion heater here, and I have an RTD probe that's measuring the temperature of the water. I'll be executing the PID on the XL4. We'll use an on-off control or a digital output from the PID loop. That will run through a solid-state relay that is controlling the heater. So let's look at how we set that up in Cscape. Here's my PID. I'm using the Autotune option as well as the ISA option, and I'm using variable-based advanced ladder. Let's look at our Autotune settings. I've assigned a start bit and a done bit and some boolean variables for the Autotune function. I'll tune all 3 elements P, I, and D. From a controller response standpoint, I'll choose medium, and for noise filtering, I'll select the minimum because I'm not concerned about electrical noise causing my process variable, which is my temperature, to fluctuate a lot. I'll tune at the full set point, not 2/3 of a set point. I might check that if I was concerned that a big overshoot at my full set point could cause a problem for my machine while I'm tuning. Now let's take a look at the tuning page. So here's what I have set up on my tuning page. I don't have any of the coefficients set yet for P, I, and D. The auto-tuning will give me a starting point for that. My sample period is 100 milliseconds. No bias has been configured, and I don't have any deadband upper or lower configured. You'd set a deadband if you didn't want your control value to be moving around a lot near the set point. In my case, I have a solid state relay controlling a heater, and I have no concerns about any kind of mechanical wear of my devices, so therefore I'm not concerned about a few extra cycles on the solid state relay, and I won't set a deadband. My upper clamp is 32,000 and my lower clamp is minus 32,000. Those have to be set that way if you're using a digital output to control a PID loop. I'm leaving error term, slew time, output polarity and derivative all at default. And I've enabled PWM, which is indicating I'm using a digital output to control my process. I'm setting the cycle time at 0 because I'm not concerned about cycles that happen frequently on my solid state relay. Even though the output is on or an off, the OCS PID loop is still doing an integer-based control value calculation. If that value happens to be below 0, then my digital output will be off. And if the control value calculation results in a 0 or higher, then my output will be on. During the tune, we can monitor what's happening on these bar graphs. In my case, my process variable and set point are scaled to the point where they won't go above 8,000. So I'll narrow my range. Now I'm ready to start my tune, so I'll go back to my OCS setup. Here I'm in manual mode and my heater is enabled. I'll set my set point for tuning at 60 degrees Celsius. Currently my water before heating is about 17.7 degrees Celsius. I'll go to the tuning screen and I'll begin the tune. You'll notice my SSR is on. So here the OCS will run the process to the set point and then a few degrees above the set point. Then it will drop back down below the set point to a few degrees below the set point, and it will do that 3 times. At the end of those 3 cycles, it will come up with a set of coefficients for P, I, and D. And now, as you can see, the temperature has started to move. So that's been running for a short while. While we're waiting, I'll put our tuning screen on display here, and then I'll switch from our tuning window to a chart. And then we'll wait till we approach the set point. Once we're a little bit above the set point, it turns off. So in this case, after 0.3 degrees Celsius, we've turned off the SSR. The temperature continues to increase slightly because of inertia before heading down. We need to go below the set point by a similar amount before this cycle will be complete. You'll notice that the solid state relay turned back on again once we got below the set point by a few tenths of a degree. So we're now on the second cycle of the auto-tune experiment. This is our last cycle and the value is going down. As soon as we get below the set point by 0.2 or 0.3 degrees, the auto-tune should be complete. You can see the done bit comes on. As soon as I turn off the start auto-tune button, you'll see the done bit goes off. Going back to Seascape, now that we're done auto-tuning, I need to close this window and reopen it again, and then I can see my suggested tuning parameters that are now in place. The next step is to test these because there's no guarantee that they're going to work, although they usually work well. We may also be able to improve them through some manual tweaking. So the first thing we need to do is test these and see how well they work. So back on my setup, I'll switch into automatic mode and we'll see what happens. I'll leave my tuning screen and switch into automatic mode. Now these parameters that were just calculated are being put to the test and we'll see how they go. Here we're actually getting further away from the set point, so that's a concern. And if it continues, then we may have a situation where the integral term is creating problems. That's not unusual in some applications. So let's go back to Seascape and look at that. Here I'm looking at the control value calculation, and as long as it's negative, the output is off. Every once in a while it'll pop on for a short second of time, but we're continuing to get further and further away from our set point. So what I'll do now is clear out this integral term by typing a 0 and hitting update controller. Immediately my output turned on, and my control value calculation went to the maximum immediately. So that's an indication that it was my integral term preventing it from staying on long enough to get closer to the set point. Going back to the setup, hopefully we can see after we've come over the inertia of the water, we'll be able to see the temperature climbing up instead of down. You can see that now. The solid state relay is on longer and we are now headed the right direction in terms of temperature. So let's watch this and see how we do as we approach the set point. We're approaching the set point and let's see what kind of overshoot we get. So it looks like 6 or 7 tenths of a degree was our overshoot on this first time through. So now let's see what it looks like on the bottom side of the set point. It's about 0.75. So it looks like we're within about 1.5 degrees Celsius around the set point. We'll watch it for a while and see how it does. The next thing I'll try is see if increasing our derivative term makes a difference. To really see if that makes a difference or not, I'll double it. So I'll set it to 90 for instance. I'll hit update controller and we'll see what kind of impact that has. It doesn't appear to be helping, and if anything, it's taking it in the other direction. So I'll let it go up through this cycle, and then I'll try reducing it instead. So back in Seascape, here it was 45, and originally I doubled it to 90. Next I'll try dropping that down to 20 for example, to see if that offers an improvement or not. But I'll wait a couple of minutes before I do that. Normally I would let this run for longer, but for the purposes of time with our demonstration, I've come to the conclusion that these changes to the derivative have not made a difference in a positive direction. I'll go back to the original coefficient value after the auto-tune, and I would imagine we'll settle back at about plus or minus 0.7. One thing to note is that I haven't played around with the proportional term at all. If I go through and do a calculation on the different proportional terms I might be interested in using, basically with the calculation I came up with, 64 was about the largest proportional term I wanted to use. So I don't think increasing it above 64 will make much of a difference. It might save a few seconds in heating the water from the beginning, but it might also have a negative impact on how tight we are for our overshoot. So to summarize, for at least this reasonable tune where I'm plus or minus 0.7, I took the tuning parameters that were suggested or found during the auto-tuning, and then after trying them out and seeing that we were unable to use those parameters exactly, I basically zeroed out the integral term because it was obvious that we were in a runaway situation in both directions. So by zeroing out the integral term, we got things to plus or minus 0.7 degrees. And then other things I've tried so far haven't improved anything. As I let this run, it will settle back again to where we were when we started. The most important thing about this video is the process that you go through when tuning a PID loop, where you're starting with an auto-tune, getting through the auto-tune, getting to the point where you're making manual adjustments, checking to see how those are doing, and then taking it from there until you're satisfied with the results. That concludes our demonstration for today. Thank you for joining me for today's tutorial, and the Q&A session will begin shortly.
Okay, a bit more in depth on the PID than our original PID webinar. There was a previous one if you'd like to look back on that one as well. Not seeing any questions as current. So if you see my screen now, you will see the upcoming webinars. So we are booked in up to the 24th. There will be a gap before the installing your OCS as we would be in the SBS show in Nuremberg. Okay, I think that's all there is for today. Thank you all for joining us, and we do hope to see you again.